Hi guys, good evening. Right, so what I was thinking on when I put this presentation, started putting this presentation together, which has just literally been put together, was I do a lot of FSAs, and I have been for a long period of time, and I just thought I'd maybe start sharing the sort of common things I come across, and I think that some of them are clear for common errors. Some of them times there are points of debate. Different people have different interpretations, and I thought, the more I thought about it, the more I could do this for lots of different subjects within the life cycle, and maybe that's why I've said it's a presentation series. So I think I might do a few more of these if it goes well today. Let's see. So firstly, I'm going to have to make a little bit of excuse to say that this is new. I've not done this presentation before. I say I've literally just made it, so I might be a little bit rough around the edges when it comes to presenting it. So let me tell you a little bit about myself. So I, like a lot of people, I'm sure in here, I've got an ICI Wilton background. I was there for 10 years, time served TIFI, and I did various other roles at ICI Wilton. And during that period, I did day release, and I did 2 H&Cs and a degree in electrical electronics. I saw the writing on the board. You can see, I knew they could see the way things were going, and I decided to take a jump, and I went to Tek. I don't know if anyone remembers Tek. They used to make flow computers. I went there for 5 years, and then I joined what was initially Amoco, but then became BP. And I was there for 19 years, doing various different roles, but for very early on, I started getting involved in functional safety. My first exposure was back in the late 90s, and I think it was, and I don't know if this is right, but I'm sure it was called BS 1508 then, rather than 61508. So that was when we built a control the safety system, and we did the safety system to that standard, or tried our best to do it to the standard. And it was such a foreign standard at the time, because it was completely new. We were used to sort of building things to TUV standard. So anyway, but I say that was my start, and I said 19 years later, I was acting as an internal consultant in BP, and then my excuse to come back up to live back in Teesside was I became the midstream technical authority, which included CATS and Forties Pipeline, Southern Vore, and that got me back into Teesside, and then sold CATS off, and then I set up my own business as a consultant. So I've been doing FSA assessing as a role since 2007. I was originally worked with guys called Mervyn Curry and Bill Black. I don't know if anyone knows these people, but BP back in then didn't have an FSA process and functional safety assessment process, and so we developed one, and then I started to implement it. I've been implementing it now, using FSAs, doing FSAs for 16 years. And in that time, I've seen all sorts of good sites and bad sites. I would say I've done most offshore platforms in the North Sea, both in the Norwegian sector and the UK, and also other places around the world. Okay, so wrong way. So this presentation, we're going to talk about my experience with the SRS, and specifically, we're going to compare what the SRS objectives are and the way the SRS should be implemented. We're going to talk about the define the purpose of the SRS, and and we're going to have specific errors, typical errors and misinterpretations and so on. Now, I brought this sheet, which I'll pass around, so if you could just pass them around. No, it's not a shit test. What it is, we won't have the time to look at all of them, so I'm going to ask you to have a look at them and tell me which ones you want to look at, okay? And we're also going to challenge a few SRS requirements as well. And then finally we're going to talk about, well, who is responsible for the SRS? Who should develop it and who should maintain it? Okay, so now the first thing I always like to say about BS 61511 is it's to remember that this standard was developed by humans. And it was a humans from an international committee. One of my colleagues I used to work with, Bill Black, was on that original committee. And one thing I learned was how it wasn't sort of a meeting of minds, but more sort of like a war of competing, ideas and competing viewpoints. From that, I know that it has, it came from a varied outlooks from the various different international teams. Individual biases and personalities are built into that standard. Varied competencies of the people there, and there was national, there was company and individual objectives. There was various opinions and differing understandings of terminology. But overall, the BSEN 61511 may not be perfect, but it's not far off, and I do like it. So we're going to talk about the SRS. Now, I've just taken this is straight from the bit underneath is straight from the standard, and the key thing about an SRS, it is a requirement specification for the whole of the SIS. So SIFs are obviously one part of that SRS, but obviously you've got the safety logic solver. Some people take different approaches. All of them are valid. Some of them take, just focus on the SIFs and try to put all this information about the safety logic solver into the SIFs. Others split off the SIF, they split off the SIFs and have the safety logic solver on a separate requirement document, and that's perfectly valid as well, as long as it makes sense. In fact, often that's the easiest easiest way to do it, particularly on big sites. Now, I'm going to on this because of time restrictions. I'm going to focus purely on the SIF SRS requirements, which tend to be focused in 10.32 of the specification, and so it's just because you could go on forever. Now, at times you'll see me using percentages. Whenever I use percentages, this is my view. Okay, it's not based on any scientific or market research. It's just my view and what I've experienced and what I expect to see. Probability of if I go to a new site, what's the probability it's going to be compliant? What's the probability? These would be the figures I would sort of have in mind. So, how often would I expect to see a 100% compliant SRS? Well, I've never seen one. Simple as that. And I don't even think it's feasible. Even I do functional safety management systems for customers, and I put together templates for an SRS, and I know I'm making compromises when I do these templates, because it's there's elements of the wording in the SRS which is difficult to achieve sometimes, or is not clear. So we do our best, but 10% I adequately compliant straight away. 20% needed some minor adjustments. I'll often raise some minor actions on them. 50%, the vast majority of them, will it miss some important items, which we'll be talking about, or they'll contain additional information that's not required in the SRS. So, and we'll talk about that. And 20%, unfortunately, are just not suitable. They just miss the point completely. It's getting less that, you know, if I was doing this talk 10 years ago, that might more have been like 40%. So overall, every time I go to a site, it is getting better. All right, now, one of the things that's slowing things down are software tools. Slowing compliance down is software tools. I've not come across any good software tools that provide good compliance to the SRS. In fact, quite the opposite. I often find that they start off with a good procedure, good template, then they buy the software tool, and it all goes to pot. Okay, so what is an SRS, and you know, what should be in it? Well, the clue's in the name, really, isn't it? Safety Requirement Specification. I don't think you can get clearer than that. You know, it is a specification of safety requirements. Maybe I could change the wording around. The SRS is necessary to success. You know, what the SRS does is specifies the requirements necessary to successfully protect against a specific hazard event, with an appropriate level of integrity, as required by the from your LOPA or the mechanism you've used to identify that integrity. And it's made up of 6 sort of groupings of data. It's functional requirements to mitigate the hazard scenario, performance criteria required to mitigate the hazard scenario, function and response requirements to failure, and requirements to enable operating and maintenance and test coverage, and also environmental conditions. So that's hardware can be selected for the for the environment, and a reliability criteria to align with business or safety requirements. So they're the 6 things. Now I've got a new slide, or just the safety requirements are the basis on which the safe must be designed, installed, and operated, against which all other phases from that point onwards will be verified or validated. So this slide, I've sort of put all the requirements of 10.32 into these groupings, and it sort of helps, I think, demonstrate from a viewpoint that functional safety requirements is the biggest section of a set of requirements. And that is followed by the performance criteria, and then jointly with the third place is the response to failure, and the requirements for maintenance, testing, and operating. You know, so what requirements are needed there? So I'm going to move on. So this diagram here provides you a nice clean-cut demonstration of the phases of the life cycle, up from the hazard identification all the way to operate. And what we see is you start off with your hazard identification, you allocate your risk, and you define your integrity of your safety system. You set your safety requirements, and that's a stop point. After that, you design, you install, and you operate, and you keep coming back, and you keep validating and verifying to that SRS. Okay? Now, now that seems straightforward, but how many people include design information in their SRS? And I would say there's a lot. You know, so yes, and the SRS should not include design or as-built specification data. Or engineering practice requirements. It's not the right place. So if you go on SRS, please try and avoid things like specification of components. We don't need to know the make and the model of the components. It is not a requirement. It's just the requirement is to have a temperature sensor. You know, it is not. It doesn't matter what so long as the selected device meets all the other criteria items in the SRS. It doesn't matter what make or model it is. And the SRS should really try and stay as fixed as possible, so that is not impacted by future design changes and so on. You don't need to include design configuration of instrument settings that are not critical to the safety function. It should include the design architecture of the safety logic solver. It doesn't matter whether the safety logic solver is 2 out of 3 or 1 out of 2 D. You know, as long as it meets the integrity requirements, that doesn't matter. Calculated and achieved performance of the design. Now, I know a lot of people put this sort of information in because it is nice to see the next to each other, your target and what you've achieved. It makes, you know, oh, yes, I can see, I can do that. But don't do it in the SRS, because the SRS means every time you change the design and you change that value, you've got to go and revise your SRS. Calculated proof test intervals. Proof test interval in the thing is more to do with what is the required target proof test interval for that site, for that business, not what can it achieve, what is the required proof test interval to meet the integrity. Okay. So you can design your system to that. I'll give you an example, and we may talk about it again later, depending on which ones you pick. I'm currently working on a project, and they've set out a turnaround period of 6 years. So that's for valves. It's a single stream site. It's going to cost them a lot of money every time they turn around, and every 6 years, that's when they're going to do most of the valves. Check do a full stroke test, probably even pull them out every 6 years. So that means they have to design them SIF loops to maintain an integrity for 6 years without doing a full valve stroke test. It's achievable. They've shown it's achievable, but it's not particularly what you would want. But but for them, it's worth it. It's worth to spend extra money on things like partial stroke testing and whatever. But you see how that's the target. That's 6 years as the target. Set requirements not associated with achieving or sustaining safety integrity. As I said, I've seen all sorts of things in SRSs which have nothing, more to do, should be in engineering practices, must be made with these wires, this specification of cabling or whatever it might be. It's what should be in the engineering practice, not in the SRS. It's not part of its safety function. And record initial as new performance results. Again, I've only seen that once, but I thought I'd mention it because it was unusual to see, and I could see why they were doing it. They did it because they had nowhere else to store that data. What they'd done is they'd built this brand new plant, and they decided, we want to keep it for prosperity, as new data, so as new performance, so we can achieve with brand new equipment, and then later on we can test against them values. I could see their point of view, but it wasn't the right place to put it. It was good data, like all the rest of these design information. It's all good data, but there's other places to put this information. This is what it looks like when you do start mixing design information, as-built information, and so on into the SRS. What you're getting is continuous feedback. It means every time you do a modification, you're starting to change the SRS. So you've got, in theory, a moving target all the time. Every time what it wants to be is you can change that design. If the plant burns down and you build it with all new equipment, all different makes and models, the SRS shouldn't change. And you should be able to still meet them that SRS requirements. That's the ideal. So I do collect the data, put the data in the right place. Instrument data sheets and so on. All these places are really important. Maintenance management systems. I know that some people do say, well, we end up with the key, what's the key? I want to be able to compare the key data. I want to be able to see the key data of the design. I want to see the key data, associated with the operator, whatever. And so what they do is they create a SIF register. It's a collation, just like the safety requirement specification is a collation of data that comes from your hazard information, from your risk allocation, and from other sources. The SIF register is a collection of key data from your phases that are upstream. Sometimes it's called something else, but SIF register is becoming quite common in audits. I like it. I do like it when I see it, but I do also emphasise to them it creates an excessive data duplication, requires a lot of resource and intensive information control because you can soon get this out of control. What tends to happen is people start keeping the SIF register up to date, but forget about maintaining the other documents like the instrument data sheets and so on. So you want to. So if you're going to do it, great, but you just be prepared to manage it. Oops, right. Right, so I have a question for you guys. A wet leg transmitter is to be used in a SIF. However, during the winter, it's possible for the wet leg to freeze. To avoid this dangerous failure, heat tracing is required. Should the requirements of heat tracing be in a safety requirement? Is anyone going to be brave enough to say yes or no?
Absolutely, yes, because it becomes major survival requirements.
I'd say no, because that's a means of achieving what you want to achieve. It's not actually what you want to achieve.
Yes, yes, you're right. So it is no. However, the reason I put this one down, it wasn't particularly this example, but it was something very similar to this. Only last week, I nearly got this wrong. And I nearly, as you said, oh yeah, no, it was to do with heat tracing. I said, yeah, well, that's a requirement. Without it, it wouldn't. And I thought, no. If you change that, because I have to test myself. I've got little rules I test myself with. If I change that instrument no longer needs heat tracing, but it meets the environment requirements, I'm okay. Therefore, as long as it meets the environment, and that's the safety requirements, the heat tracing is just a mechanism of achieving that. So it's no in this case.
Which document would you store it? Which document would you store it?
The requirement for heat tracing.
It's a fundamental requirement. It needs to be validated.
You validate it to the SRS.
So which document would you hold it in from a functional safety point of view for that specification?
Well, it would. Yeah. I mean, the fact that it goes into electrical documents that it's there, and in your proof test you would check that it works, particularly it's switched on. You may have an inspection routine to ensure that these things are switched on. That would be part of your verification that you are meeting the environmental requirements. Do you see what I'm saying?
No, I didn't.
Yeah.
It's an insource. It has to fit
Yeah.
in validation.
Yeah.
It has to fit in your proof testing. So I need a way for the design engineer to make sure that he doesn't miss it.
Yeah.
From a functional
I agree.
perspective, because it's those documents it comes back into.
Yeah.
It's just an interesting
But you see,
I would go yes, I would want it in.
Yeah, but that's yeah, and the reason is, and I think you pointed a good one out. There.
It's that ancillary clause, isn't it?
It's that bit about here's something we need, but where do I store that data? Yeah, and this is where it's so easy to put in the SRS.
See, I advocate a test strategy which isn't documented in the standard, and that's what I would use.
You're right.
Test
Okay.
strategy lets me draw those things out, so
Yeah.
I have somewhere to document it. So I look at all the amounts of the
Yeah.
individual components. But yeah, that was just a question.
Yeah.
So I know it comes back in at that next bit.
Yeah.
And I do need it.
Okay, so so I thought we could. I said, I know we could push. We'll be pushed for time. How long do I have, by the way? And I will.
We normally finish around 7.
Okay, that's fine. So we'll do about. Let's do about. Let's at least do 2 of these. Okay, we'll see how we're doing for time. So there's, the first 7 on your sheet. Does anyone want to have a pick one out and say, oh yeah, let's have a talk about that one? Number 5. So 1, 2, 3, 4, 5. That's the output criteria for successful operation, yeah? Okay. So 10.3.2 dot, and I put letters L. It's obviously on the standard, it's just a bullet point.
That's very weak in the standard.
It is. A description of the SIF process output actions and criteria for successful operation, and an example leakage rate. Now, this is something that I see a lot. And I see things like Tate shut off, yes, no. Okay, I see things like valve shut off, and the people put in class 4, you know, whatever they're going to purchase, you know, the class of valve. But these problems, and one of the things I often see, I only see stuff for valves. And yet valves are not always most of the time they are the final element, but not always. So, you know, the first thing is I would say is, what about pumps? You know, how, you know, there's sometimes you may have specifications that are to do with the pumps, like and in the options there. Sometimes a pump might need to have free run capability, so that doesn't create a hydraulic shock. The next thing is tight shut off. The use of the word tight shut off, and I see this a lot. What does it mean? What does tight shut off mean? What can if I wanted to do if I wanted to measure that, what is it? It's a term we use, but I can't find somebody says, oh yeah, that's this amount of leakage. You know, bubble tight. I hear people say bubble tight.
It's something that comes from before you have classes.
Yeah, exactly. Yeah.
A tight shut off or not a tight shut off. Generally, it ball valve rather than a globe valve. You know.
Yeah.
But classes have sort of overtaken that.
Exactly. Yeah. At least now it's measurable. With the classes, it's measurable. It gives you a value, you know. And but yeah, the tight shut off. Remember the SRS is something you have to verify and validate too. So you've got to have something that's measurable. And the use of the class. Now, when I use a class, I hear different stories. So I've tried to put them down here. Sometimes people put, I want class B. They use other terms because obviously there's different standards for this. They'll say, I want class B, but I'm going to buy class A. And that causes confusion later on. In 10 years' time, the engineers have all gone, hang on a moment, pull this out, it's a class A. But the SRS says a class B. Must be wrong. I'll change that, class A. And, or I see a case where it says class A in the SRS, and they put a class A valve in, and they pull it out to overhaul it and test it. They do a pre-test before the overhaul. You know, 10, 15 years later, and some sites 20 years later. I know that's not right, but it happens. And of course, it doesn't pass. Because it's not going to be as new condition, but doesn't mean that it wasn't safe. Yeah? So, so it may be that a leakage from that valve was still acceptable. And for this reason, I always try to suggest that they put litres per hour at the process conditions of their site. I mean, that's another point, actually. What I find is they'll say, oh, yeah, we want class A or class B, or whatever it might be. And let's say it's because we want less than 0.1 of a litre per hour. for example. And but forget that the classes is based on a different process conditions to your process conditions. So it might that when they test it, you know, oh yeah, it's achieved it's achieved that 0.1 litres per hour, whatever it is. Might be tested at 10 bar G or even less, and yet your plant is at 70 bar G. So what's the correlation? It's a really difficult. But if you say, I want to achieve, you know, 1 litre an hour, I want it no more than 1 litre an hour at this pressure, this temperature, whatever it might be, you know, particularly the air pressure, differential pressure, I should say, then it means that when you come to do your pre-overhaul test, you've got something that you can test against, and you've got values that make sense and correlate to that valve and that valve's purpose in life. Okay. Right. Any others? Oh, actually, we did not. That didn't take too long. Might do 3.
You do I, 10.32I.
I, yep. Okay, so response time requirements for each valve to bring the process to a safe state within the process safety time. Well, there's a couple of things on this one. So, firstly, I may see process safety time. I may see safe response time 12 seconds, and that is you know, and they've set a value that is less than the process safety time. Nothing wrong with that. I may see a final element 10 seconds. Again, a value less than the process safety time. Now, the problem with when I often see just final element listed, the problem with just listing the final element is you're missing out the rest of the SIF. And it is to do with the SIF response time. Now, I know that the valve is the longest takes the longest time of the SIF. You know, you're talking maybe half a second for your sensor, and another it was half a second for your logic solver, sometimes a bit longer. So you're only talking extra second, but it's if you're doing something that 1 second may be important in some applications. So again, I would say always give the SIF response time that you're after. It's the first thing. But the next thing I want to talk about is the problem is defining what the process safety time is. Now, the standard says that the process safety time is the time between the failure occurring, a failure that can cause a potential hazard, and the point at which the hazard event occurs should the SIF fail. It's that first bit, the failure occurring. That's a variable, and it's a variable that we can't measure. We don't know if when the BPCS, it might be, let's say, if you had a tank and your normal operating envelope is, say, 30 to 60%. It could be that the failure could occur at 50%. It could occur at 40%. You don't know, and you're not going to know it until it hits the trip point, basically. And so I always encourage the people I work, the companies I work for, to in their functional safety management to redefine this. And to say it's the time period between the process conditions exceeding the defined trip setting and the occurrence of the hazardous event if the SIF is not, if the SIF doesn't perform. So change the wording slightly, makes it more measurable, and now you can start to say, if you know what the process safety time is, you can now say we've got to be less than that. So a good result would be for me to see something like SIF to be less, less than 12 seconds, based on a percentage of the process safety time. So, for example, in BP, that is 50% of the process safety time. So they say, instead of saying it's just got to be below 50%, below the process safety time, they actually BP specifies in their management system, functional safety management system, that it must be half the process safety time. Nothing wrong with it being 90%, except it's going to be harder to maintain that. That's all. But from a normative requirement point of view, as long as you're less than process safety time, I would never fail you. I would never give you an action on it. I would just raise that. You're just going to make life hard on yourself if you get close to your process safety time. And the SRS should also reference the process safety time calculation sheet. So that's also, I think, a key point is define that, because that's source bit of information, where that's coming from. The SRS often has you often put a document section in the SRS that just refers to the documents that the information comes from. And that's good. That's the phase 1 and phase 2 type documents. So 10.3.2.R, failure modes for each SIF and desired response of the SIS. Now, I ignore the mitigated word, that should be there. So 60 to 70% of SRSs that I look at provide a basic statement regarding they'll say, oh, our valve must be fail-safe, or our sensor will go upscale, okay, on failure. But they don't define the failure modes. I know it's difficult because there's often lots of failure modes, but they don't define any failure modes. 20% of the SRSs will provide some sort of details on the failure modes and may state an alarm is raised. But of them 20%, none of them will actually say which alarm is raised. They'll just say an alarm, but don't say which alarm. Only 10% or less than 10% will actually identify that alarm that's raised when a fault occurs. And that's actually quite an important bit of information. So firstly, it is important to understand what failure modes we are what we are looking for, what sort of failures we're looking for, and how we're going to deal with them. So, I would say that we need to define the failure modes that are diagnosed by the device or the SIS. Which of them failure modes will result in the SIF going to a safe state, and which of them will identify an alarm. And if you do identify an alarm that says, oh, okay, we've got a dangerous failure here, then you've also got to put a requirement in, which is 10.3.2.x, which I'm going to go to next. So this X one is the specification of any action necessary to achieve and maintain a safe state of the process in the event of faults being detected in the SRS, taking into account relevant human factors. So this is now 50, again. More than 50% do not recognise that any human action in their SRSs. They don't identify it, because if they haven't even stated what the alarm is, it's unlikely to say what the human action is. Or they'll say, oh, well, it's in the alarm response manual. Well, the alarm response manual needs to get the information from somewhere. That's how the alarm response manual is often is often the thing in which you say, we've got this, and that verifies that we are doing what the SRS says for the human action. And more than 90% never take into account relevant human factors. This is a growing subject. So concerns raised here are human actions are rarely included in the SRS, and it has been argued that such requirements cannot be validated and verified. it is, and a note to say, it is the operator and maintenance, inspection and test procedures and tools, example the arm, in place that do verify these requirements. You know, it's not a case of checking that the guy does what he's doing. He's making sure that he's got the information, the tools that are going to put him in the right direction. And things like, you know, the alarm being in the right priority. So the SRS should define the required operator response to a dangerous diagnostic alarm, including any time limits, and any actions identified by the any actions identified by human error analysis that are required to manage performance, influence, and factors. So, in other words, because if anything that's got a human action that is relative to the integrity of the SIF, and if that SIF is related to a major accident hazard, then it really, under COMA, should have a human error analysis. And the human error analysis identifies the performance, influence, and factors that you try to identify actions of how you can control them. And I've just put some guidance in there. So does that make sense? Yeah? That's how you meet that last bit. Because I often get asked most of all, taking account of relevant human factors. What does that mean? So it means doing a human error analysis on various parts. Okay. Oops, I've accidentally come up to the presentation there. I meant to go up to there. Right, we'll move on from this. Challenging SRS requirements. So I've now got 3, which I think are the most challenging requirements. And you mentioned the first one, I think, C, so I'll go straight to that. Okay, requirements to identify and take account of common cause failures. Okay, now, so I struggle with these 3. Let's make it clear. The standard and the the standard mentions common cause failures 27 times. So it obviously was important to either the IEC committee or particularly one of them. Okay, so it is mentioned quite a lot, and it is an important element. Now, the identification of common cause, there's two areas in which common cause failures are talked about in the standard, and we need to be clear that it's not clearly specified this way, but it needs to be understood. There's the identification of common cause failures in what we call phase 2, which is, and these requirements are identified in clauses 9.26 and 27 and 9.4, and they're basically saying that you should really do a quantitative or qualitative common cause analysis to ensure that your SIF is to basically make a judgment on the common cause relationship of your SIF against other layers of protection or the initiating cause. Okay, the difference, you do most of the time you do a qualitative analysis. In fact, most people don't even bother with that, but you should do, in most cases, you're supposed to do a qualitative analysis, which is just a check sheet. And only if the total cumulative risk reduction of all your instrument layers exceeds 10,000 risk reduction factor, then you should do a quantitative common cause analysis. I've never seen one yet. And I would say the truth, I wouldn't even know how to put one together myself. But I do provide my customers with qualitative common cause analysis for phase 2. Now, but the words in this clause 10.3.2, they're not really asking for that. They're not. What I would say is any actions that came out of that process in phase 2, that where needed safety requirements should go in the SRS. I would agree with that, but that's not what the clause is saying, because it says requirement to identify. In other words, it's the future requirements to identify new ones. So it can only be talking about the design common cause analysis. Now that's the common cause failures, but that's actually between the say multiple channels of a SIF. So if you've got three transmitters in a voted architecture, so what is the common cause failures between them three? If they're all the same makes, they're the same models, and so on, and they're all connected to the same place. So it suggests it's something to do with the future, and so it's all like saying, tell me, set out a requirement to do that, to set out a requirement to do that common cause, have a procedure or something. It doesn't seem right. The other part of that statement says, and take account of common cause failures. And when you take account of it, do you use a beta factor? For them type of common cause failures. And you have a beta, and you determine your beta factor. There's a method. There's various methods. 61508. The sixth one, 6 documents. It suggests a method, but there's other ones which are pushed by people like David Smith and so on. So, but to me, that's design data. That's design information, and it's already got a place. It belongs. It's already defined. You do that as part of your SIF reliability study. You don't need it. You don't need to specify to do it in the SRS. It doesn't make sense. So that's one of the ones I don't particularly like. Yeah?
I think it's one's a bit like,
yeah.
Common board and common cause. I think the only thing I pick up on that, I think it's trying to drive at those process things just to make sure that's the place where you're trying to...
It is. I think it's there because it's trying to drive that thing. You must be thinking of common cause. Common cause. That's what you must be thinking of, because there was obviously an emphasis in the committee.
I think it's
to focus.
Trying to push on multiple process tappings. So if you're trying to use a common one, that's
well,
you need to drive that.
Yeah. Well. That should be done in phase 2 as part of your common cause analysis. Is the process tappings, is it shared with the BPCS initiating cause? Is it shared with another instrument of layer protection? And it's also done as part of your you should also do one of your design any road in phase 4. It's not really there's nothing you can validate to. Do you know what I mean? Nothing to say. In other words, starting to get into engineering practices if you start saying make sure in your SRS that you have 3 separate tapping points. That starts getting into engineering practices. Okay, I'll do this one. This is another one because I get this one is raised a lot. A definition of any individual safe process states which, when occurring concurrently, create a separate hazard. Okay, that's another one. Well, to me, again, it's the wording, a definition. What's it asking for? It's asking you really to do a hazard analysis, some sort of hazard analysis there. But that's phase 1. So, I'll give an example of this. An example would be a flare system. So if you had 2 SIFs going off at the same time on two different parts of the plant. Let's say you got train 1 and train 2. And if they went off at the same time and both sent all the gas to a flare stack, you could overload the flare system. And there's I know there's sites in our local area that could occur. And so this would be a case where you got two potential perfectly good safety functions, but if they came together, would create a new hazard scenario. Now, that to me should be identified as part of your hazard study. That's what the hazard study is there for, and it should be looked at in phase 1 as a potential hazard. What happens if we train 1 and train 2 just blow down at the same time? we know we have this now. I know we have this now. They'll often do flare studies and so on. And then whatever comes out of the hazard study would then go, like the other hazard would then be analysed, go through its process of allocating, do we need a SIF? And if you do a function, then that function should be treated separately. So, and typically the SIF won't be, it's not going to be a normal SIF because it's going to be a new bit of logic. It's going to say, let's put a bit of logic into the safety logic solver that says, if this one's triggered, let's have a timer to prevent this one triggering, at least for, let's say, 30 seconds. So they do these, to achieve, and that 30 seconds timer, it's not part of either one of the SIFs. That function is not just, but it's really in many respects it's its own standalone function. It doesn't have a sense, it doesn't have a final element because it's all in a thing, but it should be defined. And that's where it's them sort of situations where a safety logic solver SRS comes in handy because that's where I find it's a good place to identify it. But anyways, it's just that's an example of again another one that's another one that's often misunderstood, and it is easy to misunderstand it, and it's often and say really, well, hang on a moment, it's just another hazard. We've got a process, phase 1, hazard, identification, phase 2, allocate the risks. We don't need another prompt here to say, oh, we need to do a hazard study again. Okay, I'll move on from this. See, I'm quite happy to provide all the slides so that if you want to read the other ones, please feel free. I think I put enough words in so you don't need me to talk about it. I just want to finally finish off with SRS ownership. So let's just remember that all persons, departments, organisations or other units which are responsible for carrying out and reviewing SIS safety lifecycle phases, or any activity really within the safety lifecycle, need to be informed who is responsible and assigned to them. So who should be responsible for the SRS? Now, I don't know if this would agree with your own experience, but I find on 40% of the sites, the instrument engineer only. He said, like, oh, you put an SRS together, and the instrument engineer does it. Okay. 30%. It's the instrument engineer, but he works alongside the process engineer, and that's becoming better. 20% is the instrument engineer coordinates with a multidisciplinary team to develop the SRS. 10% is when it's not the instrument engineer doesn't lead it, but it's actually the process safety or tech safety engineer. And nowhere do I actually find the process engineer. I've never found the process engineer responsible for developing the SRS. And yet it surprises me in some respect because before 61508, the process engineers used to produce what was called a PSR, Process Safety Requirements Specification. And that would specify a lot of this sort of information, not so much for instruments, but for relief valves and all sorts of things, final elements. Now, when it comes to maintenance, it's nearly always the instrument engineer. He's the one who's going to use it, therefore you look after it. And as I say, there's a smaller number of cases, it's the instrument engineer, but again, it's the instrument and process team work closely together. So let's consider where the data comes from. And I've used this method to look at the requirements, but this time group them into the disciplines. Who delivers these items, these pints? And you can see by far the process engineer, he has the most of them. He's the only one who can deliver on the most of these things. So the instrument engineer is going to ask the process engineer for information. And second is going to be the, obviously, it's going to come out of engineering practices, or commercial drivers, operation requirements. But the instruments, actually, delivering stuff, actually needing to put something, he doesn't have much to do at all. So the last person really putting the SRS together should be the instruments. When it comes to maintaining, again, I would try to keep it with process safety. And one of the reasons is because this frustrates me more than anything. I go to a site and you go, right, oh yeah, you review your HAZOPs, sorry. Do you review your HAZOPs? Do you review your LOPs? Yeah, they can show me them. They have, every 5 years or whatever it might be, they've reviewed the HAZOPs, they've updated it, they've rechecked the LOPs. Great. But have they updated the SRS? Nah. No, the SRS is still 15 years old, well, you can't really tell because it's changed in all this, it's got design information and it's changing all the time. But the targets, that things like integrity and so on, they haven't been updated. If it belonged to the process safety, they would just automatically do it. But what tends to happen, and I've seen this very recently on a site that I'm close to, process safety, they get the money, the finance to update the them documents, and then the money runs out, and there's no money to update the SRS, because the guys, the engineers, are often, really, really busy. They need someone else to come in and help them out. But there's no money, and therefore it just gets left. And it's like the whole point of of your HAZOP and your process for us instrument engineers is to feed into that requirement specification, and then we can make our instruments achieve it. So it's something to think about. Let's try and get. There was a time, it wasn't that long ago, where process it was. For in BP particularly, my experience was it was the instrument people who did the LOPers. I used to chair LOPers all the time. The process people didn't get involved until about 2012. And it was just because we needed the information, so we were having to go out there and actually do the LOPers. But it's getting better. That is something that is in the past, thankfully. So ideal ownership would be, as I say, either see it as a multidisciplinary team or process. It is debatable, but I'll give you my thoughts. So anyway, so that brings us just after 7 o'clock. Thank you for taking the time this evening to come out and listen to this. I hope you found it useful. I hope there's some pointers things in there, and I hope if you read it later, you'll meet some other things that you might find useful. I'll be pleased to answer any questions either tonight, or you can email me. I'm always happy to talk about these sort of things. Contact me anytime. I don't charge. Not for the